All right. Hello, everyone. Welcome to Neuron, Synaptic Transmission, and Neurotransmitters. Oh my. Ha, I think I'm clever. I am your humble guide along this journey. I am Dr. Audrey Robinson. Most of you are probably listening to this as part of your Psychopharmacology class. This covers Julian's Chapter 2, and I'm here because I love to give presentations. Just kidding. It's because I love psychopharmacology. I really do. You know, and they pay me. That's a bonus. Oh, and that's what I look like on my best days. Not today. All right, cool. Let's talk about brain organization. We kind of need a filing system for how we're going to look at this, and we're going to relate all of this back to psychoactive drugs because they act in the brain, but many of the side effects act in the peripheral nervous system, or PNS, which is going to be abbreviated throughout this presentation. And there's a great figure on page 40 in your book of this. All right, so on the left side, you have your central nervous system, which is made up of the brain, which is then divided into the hindbrain, midbrain, and forebrain, and then there are specific structures under each of those. And then you've got the spinal cord, which is like the superhighway of our body, and then our body is made up of 90 billion neurons or more. And then you have the peripheral nervous system, and these are nerves that originate in the spinal cord and then connects to the organs in the rest of our bodies. Okay, so I'm going to make you watch this video, and if you were born in the 80s like me, then maybe you grew up watching Pinky and the Brain or Animaniacs, and so there's this great song that I've loved since childhood, and I put it into every presentation that it is applicable for, so we're going to listen to the brain sing about parts of the brain.
Pinky and the brain, 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 brain.
And now, the parts of the brain, performed by the brain.
Yes. Neocortex, frontal lobe,
Brainstem,
hippocampus, neural node, right hemisphere, pons and cortex, visual,
brainstem,
Sylvian Fisher, pineal, left hemisphere, cerebellum left, cerebellum right, synapse, hypothalamus, striatum, dendrite. Axon fibers, matter gray,
brainstem,
central tegmental pathway, temporal lobe, white core matter, forebrain skull,
brainstem,
central fissure, cord spinal, parietal, diameter, meningeal medulla oblongata, and lobe limbic, microelectrodes, the brain. That ought to keep the little squirts happy. Yeah.
All right, well, so hopefully for the purposes of the YouTube video for this, that worked out and you got to watch the video and hear it. If not, click play, or you can Google Pinky and the Brain song. One of my favorites. So hopefully you didn't just fast forward the Pinky and the Brain song. Hopefully you got to see it and as a little part to give us some of the structures of the brain. All right, so now that we sang them, let's learn what they do. Okay, so we're going to start with the brain stem, and that is made up of the hindbrain and the midbrain. Midbrain's a tiny little piece. You can look at the graphics in your book. So the hindbrain's made up of the medulla oblongata, and the pons, and the cerebellum, and then the midbrain. So in the midbrain, there's a couple of structures that we need to know about. The tectum, which means roof, and those are pathways that carry sensory info, and the tegmentum, which is the floor, means the floor, and that is made up of the substantia nigra, which works with the basal ganglia, and the ventral tegmental area, or VTA, and you're going to see those words later in this presentation, so that's why we're kind of reviewing where they are now in the midbrain, and those are part of the reward circuit in the limbic system. Most of these structures contain dopamine. Bonus points to you if you recognize this graphic. It is from a funny Adam Sandler movie, and you can see medulla oblongata down there. All right, now let's talk about the forebrain, the part of it that's called the diencephalon, and that's made up of the hypothalamus and the thalamus. So the hypothalamus modulates the pituitary gland via releasing factors and is responsible for integration of our autonomic nervous system, like eating, drinking, sleeping, body temp, that sort of stuff. And then your thalamus is a relay station for everything except your olfactory. It has its own relay station. So hearing and sight and that sort of stuff. All right, then we have also in the forebrain is a area called the telencephalon, and that's made up of the basal ganglia, which also has parts called the caudate nucleus and the putamen, aka striatum, and together those are called the cerebral striatum, and then the globus pallidus, and that integrates movement for us. So with the basal ganglia, Parkinson's or Huntington's are thought to be affected, have this area affected. And then next we've got the limbic system. And so the limbic system is made up of the amygdala, which has to do with our emotion, and the hippocampus, which has to do with the formation and storing of memories. And the limbic system and the hypothalamus interact to regulate emotion and emotional expression, and it's the site of action for many psychoactive drugs. Also notable in the limbic system are the cingulate cortex, which is involved in integrating sensory, motor, visceral, motivational, and emotional formation. And then the anterior cingulate cortex, anterior meaning the front or forward, which is involved in empathy and the idea of fairness and unfairness. And then you have the posterior cingulate cortex, posterior meaning like behind, and that monitors performance during learning. So that posterior cingulate cortex is probably working right now as your brain is going, oh my gosh, all these words, sciencey things. I remember hearing this stuff before in biology. Okay, so our cerebral cortex is made up of 4 different lobes: the occipital, which is vision; temporal, which is hearing; parietal, which is our sensory perception; and then the frontal lobe, which is higher level cognitive functionings. And there's this really cool website that's linked down here, humanconnectomeproject.org, and that has lots of updated information, and they're always producing new information about the brain. What we know about the frontal lobe is we used to think like, oh, that doesn't, develop till like 18 or 20, and now we know it doesn't develop well into late 20s, totally. So just keep that in mind. That is something good to know if you are working with even early 20s or teenagers or even children. Those higher levels of cognitive functions, often called executive functioning, not totally developed. Here's a video. I'm not going to play it because now that I think about it as I'm recording this, I don't think that in the YouTube it will play a video like within a video. I think you'll just get the weird audio. So I'd like you to watch this. This is me, and this is a video. I work for Mesquite ISD. It's like my day job. And so part of what I do is support social emotional learning for the district, specifically with like the younger elementary students. And then my counterpart, Christy Davis, supports social emotional learning for secondary. So we came up with this video, and this is geared towards middle school and high school students and middle school and high school teachers to kind of teach about a basis of the brain. So they watch this video and then they do like a little mini lesson and some writing and thinking about how they can monitor themselves. Sometimes we call that metacognition, and about how they can help themselves. We say get back to green, which is like get to a calm, executive functioning kind of place where you're, where your prefrontal cortex is more in control more than your amygdala. And so I would like you to watch this just to see how these concepts can be used. There's also a version, we do lessons with as young as pre-K, and we have a cool little hindbrain model. And I'll link some resources, and there's another video after this one that you can watch, which is kind of like the kid version of it that's put out there by, not by me, but all our elementary school counselors from pre-K through 5th grade teach a hindbrain model, and we teach the kids the words prefrontal cortex, amygdala, and hippocampus. And we talk about how when they quote unquote flip their lid, then their amygdala is in control, and they have to do some things to calm their brain and their body back down to get their prefrontal cortex back in control. And we use like the analogy of a dog in a doghouse. And so we link this idea of our amygdala being in control to that fight, flight, or freeze reflex. You know, if our dog doesn't feel safe, then he might run away, he might fight and bark, or he might freeze up. And so we teach this concept to kids as young as 3 and 4. We don't expect them to necessarily remember those words, but we teach it every year, and we build on it. And scaffold, and those concepts get more and more complex until they get into high school, because we want to create humans who know that they are in control of their own brain. So this is an example of how this can be used with clients and kids. I'm not actually going to play that. Here is the other video called Why Do We Lose Control of Our Emotions? Really cool whiteboard video. It's about 6 minutes long. If you work with kids, this is a great one to share. All right, so now let's move on to synaptic transmission. So neurons plus glia equals love forever. All right. Trying this again. I had just about the whole thing recorded and then realized somewhere along the way at this slide things stopped. So, okay, here we are with neurons and glia. So hopefully some of these things are things you recognize from maybe like high school biology, or if you took a biology course in your bachelor's degree. I took biology for non-majors, so a lot of these words ring a bell, but it doesn't mean I necessarily remembered what exactly their processes were. So we're not going to discuss necessarily what everything does, but we're going to discuss how it relates to psychoactive drugs. So the soma is the cell body of the nucleus, and then inside you've got organelles, mitochondria, Golgi bodies, and one note is that the Golgi bodies are what pack the neurotransmitters and store them. So then you've got the dendrites, and on the dendrites are receptors, and then the axon transmits signal via synapse through an electrochemical process called the action potential. And those axons can be really long, go throughout the different parts of the body. So one important note is that your brain is really plastic. There is neurogenesis. We used to think that when you were born, you had all the neurons that you were going to have for the rest of your life, and then that if any of them decayed or died, then that was it. But that's not true. Actually, your neurons can be reborn and reformed, and the brain can change and grow and repair damage. It's pretty amazing, and this is especially important for like PTSD and for trauma. One other point is that on the synaptic terminals, there are a structure called synaptic vesicles, which you're going to be talking about a lot. And each have several thousand neurotransmitter molecules, and they store, those vesicles store and protect, I think like serve and protect. There's also a process called exocytosis, and that is where the transmitter is released into the cleft to the receptor. And so that's the process that a lot of our psychoactive drugs affect. So then there's also autoreceptors, and they serve as the police, and they reduce the synthesis and release of the neurotransmitters. All right, so then we have the glia, and there's several different kinds. Oligodendrocytes are the myelin sheath around the axons, and that's that fatty material. We used to think once upon a time when we were talking about like dieting, like, oh, have a low-fat diet, don't eat a lot of fat, fat's bad for you. But then what we learned is our brain actually needs the fat. It kind of like greases our brain and makes those connections work, and so actually healthy fats are really good for us. Astrocytes, These are where the nutrients and structural support lie, regulating the ionic surroundings. They modulate the rate of the signal transmission and the reuptake of neurotransmitters. You're going to hear that word reuptake a lot. And then there's the ependymal and microglial cells, and they're in charge of cleanup and pruning. So those are all the structures. All right, 2 ways to get rid of neurotransmitters. There's either a breakdown, which happens via an enzyme in the synaptic cleft. It breaks it down, turns it into a metabolite, and metabolites are then taken back up into the presynaptic neuron to be repackaged for release later. One example of this is acetylcholine, which we'll talk about. The other process is reuptake. Hey, there's that word again. The transmitter is taken back and repackaged, and this happens with dopamine, norepinephrine, and serotonin. And this is where that word reuptake, you're going to hear it, especially when we get into like antidepressants. So you have something called a selective serotonin reuptake inhibitor, and it inhibits this process. So then there's more serotonin floating around in that synaptic cleft, which means that it can then bind to those synapses. All right. So we're going to talk about specific neurotransmitters, the ones that are specific to psychoactive drugs. Neurons release specific chemical substances from their presynaptic nerve terminals, and then there's the interaction between the psychoactive drugs and the receptors on which the natural transmitters act that underlines the action of drugs. So really all the magic happens on those receptors. All right, really like this table from our book. Didn't want to have to recreate it. I don't like to take pictures of our book and just stick them in here because I want you to read your book and then use this after you've read through the chapter to kind of solidify the important parts and link these processes to other concepts. But I really liked how it had the breakdown of the different families and subfamilies, the amines or amines, amino acids, neuropeptides, peptides, purines, lipids, and gases. All right, acetylcholine. It's one of the first ones that was identified, and it functions with the PNS. It's associated with Alzheimer's because acetylcholine has profound effects on memory, so this is where we see like deficiencies. An example of a drug that affects acetylcholine is scopolamine, and it produces amnesia. And if you remember from last week, we talked about scopolamine being one of those on the skin, a patch that the drug is delivered via the skin and absorbed that way, and that is one that is often used for like cruises, for motion sickness. Interesting, the effects and how one of the side effects of the drug is the motion sickness, which is how it's often used. All right, so the action for acetylcholine is terminated by an enzyme called acetylcholinesterase. And there are 2 different kinds of inhibitors, reversible and irreversible. Irreversible are ones that have damage in the memory. And so the irreversible ones are used in like farming because they kill insects instantly. And then there's also irreversible ones that are used by the military for gases. And then there's reversible. And I wanted to point out cholinergic receptors. And so if you've ever taken any kind of cold medication, maybe a prescription, you might get a class of drug called an anticholinergic. And it's like a drying agent that kind of helps when you have a runny nose and some of that head congestion and stuff. And so it's interesting how we use something that affects acetylcholine and these cholinergic receptors in many other ways. So those receptors have 2 different kinds called muscarinic, which affect memory, arousal, attention, and analgesia, and then nicotinic, skeletal muscles, nervous system, and adrenal glands. All right, monoaminergic neurotransmitters. So these are the 4 different classes of these MAO neurotransmitters that we're going to talk about. And I'm going to have a slide for each of the first 3. I'm going to talk about peptides and transmitters on this slide because there wasn't a ton of information that we needed to know about this, but there's a lot for the others. So we're going to focus on peptides right now, which are small proteins, which are chains of amino acid molecules. And the 2 different kinds are opioid peptides, which involve endorphins, and enkephalins, which are involved in emotional states like pain perception, reward, emotional stability, and energy, like quote-unquote highs. Examples of those would be opiates, morphine, codeine, heroin. And so I want to make a note about coding here because this is a common misconception. And when I worked in pharmacy for those 6 years, drove me crazy because there is a drug. Its brand name is Vicodin, and its generic is hydrocodone. And it is not the same as codeine. Although many people call it codeine and say hydrocodone, it isn't. It's hydrocodone, which is a derivative. But many people who are allergic to codeine are not actually allergic to codone because it is a different chemical structure. So just so you know. Heroin's also one of those. I think I mentioned that. Now the other substance is substance P, and it's a gut-brain peptide. And so we talked last week about how like our gut has a major role in mental health. Well, here's one of those links, the gut-brain peptide. It has a role as a sensory transmitter, especially pain. It's affected by opioids, serotonin agonists, norepinephrine agonists. And so these peptides have a huge effect on our psychoactive medications and drugs. So one more note about this is we used to think that each neurotransmitter had its own house, like its own receptor, its own synapse, where it was released. And now we realize they're really more like apartments, and so lots of different types of neurotransmitters can be released. So there's co-release of more than one neurotransmitter at each synapse, which at first we thought they would just stand alone, and really that would be more of the exception, not the norm. All right, catecholamine transmitters. There's two different kinds, norepinephrine and dopamine. And those are in the central nervous system. And then we also have epinephrine, which is also known as adrenaline, which is in the PNS. And these are inactivated by enzymes, such as one that's pretty well known, monoamine oxidase. And there's a class of drugs, monoamine oxidase inhibitors, or MAOIs. And it's one of the original classes of like antidepressants and psychoactive drugs, and it interacts with just about everything on the planet. And if you get anything over the counter and you look at the warnings, you know, most of them say like don't take if you're pregnant, or you know, talk to your doctor if you're pregnant or nursing. And then there's always usually a warning about don't take if you're taking MAOIs. So that's what we're talking about here, are some of these transmitters. Both of these have implications in schizophrenia and Parkinson's, affective disorders, sexual activity, addiction, and ADHD. So dopamine originates in the brainstem, to the brain, to the spinal cord. It especially is active in the hypothalamus, to the pituitary glands, and that would be where hormones, it's in the release of hormones, and there is some evidence that there is impairment in these areas related to schizophrenia. And the substantia nigra, which we talked about earlier, to the basal ganglia, that pathway, and it helps to regulate movement. So Parkinson's, or side effects that mimic Parkinson's from psychoactive drugs, interfere with this process here in dopamine. And then the VTA in the midbrain, in the frontal cortex, in limbic system, that is the central reward circuit. And that is where the development of addiction, and addiction has a lot to do with the dopamine in that area. All right, norepinephrine originates in the brainstem, in the pons, to the cerebral cortex, the limbic system, the hypothalamus, and the cerebellum. You're seeing we're talking about a lot of these same structures over and over again. Travels down the spinal cord via the axon, and there's an analgesic action through that. It also produces alerting, focusing, orienting response, positive feelings of reward, and analgesia, which would be like reduction in pain feelings. All right, Indolamine transmitter. So for something to be an Indolamine transmitter, we're only talking about the serotonin one, which is abbreviated by that 5-HT. What makes it an Indolamine is the specific type of structure that is in that transmitter. And so serotonin is also synthesized by the essential amino acid tryptophan. And I brought that up because, you know, we all know tryptophan from the Thanksgiving turkey. So I thought, after I ate my Thanksgiving turkey and I'm nice and full, and if that tryptophan has that interaction with the serotonin, wonder if that has anything to do with that warm, happy feeling I have after being full of turkey, or if that's just the full belly and Black Friday shopping that starts early. Actually, turkey doesn't have a ton of tryptophan in it, really. There are lots of other foods that we get that from, like bananas. All right, so LSD resembles serotonin, and they realized that those hallucinations mimic serotonin, and so when you have serotonin toxicity, that looks a lot like LSD. Serotonin is found in the upper brainstem and the pons in the medulla, plays a role in depression, anxiety, OCD, panic, phobia, sleep, sex, cardiovascular function, regulation of body temperature. So we talked earlier about that SSRI, selective serotonin reuptake inhibitors. So they inhibit the reuptake of serotonin, which means there's more of it floating around. All right, amino acid neurotransmitters, glutamic acid or glutamate. It's an excitatory acid, and it's the precursor for the GABA, that gamma aminobutyric acid, which is an inhibitor. So glutamate's a non-essential amino. It's easily synthesized, doesn't readily pass that blood-brain barrier. We can find high concentrations of it in the cerebral cortex, hippocampus, basal ganglia, septum, and amygdala. And there's two different types of receptors, non-NMDA and NMDA receptors, which happen to be blocked by magnesium. So a lot of people, spout that magnesium, especially certain types, there's different formulations of magnesium, help to provide calm, and you can find different ones on the market. So this is why there's that thought that magnesium can help be calming, because it calms and blocks those receptors that the glutamate attaches to. It's also involved in cognitive processes. Just so you know, too much glutamate can lead to neuron destruction. A little bit's a good thing, too much is a bad thing. So then we have GABA. It's inhibitory, and it's formed by glutamate plus an enzyme called glutamic acid decarboxylase. It's found in the brain and the spinal cord. There's two types, A and B. A is the fast type, B is the slow type, and barbiturates and benzodiazepine facilitate the action of this, so that's why they have those calming effects. Most other amino acids besides these two don't really act as neurotransmitters. That's why we're only really talking about these two. All right, as always, I like to have a why in every presentation. Like, why in the world are we learning this stuff? More than it's just cool and you can talk to all your friends and sound super smart. It actually has implications for our clients, because you are your brain and you are in control. Your brain is you, you are your brain. We can help our clients to understand that they really are in control. We can help them with understanding maybe some of these processes. When they have side effects with medication, we know maybe the regions that these are related to, the effects that these things can have. We know our body is all interconnected, so we can't really, as much as we like to pull out our thoughts and our feelings and our behaviors and look at them and analyze them individually, we're so interconnected. And knowing these processes and that can help us to normalize things for our client. You can help your clients be in control. All right, this was a lengthy one. Thanks for watching. And here's the resources. The end.